Okay, any questions before we roll? Okay, so we talked about this LU factorization last time. By the way, yeah, so I'll tell you the schedule. Quizzes after this class today, or after my other class, I will make the next quiz live as usual. It will be due Friday at 5 o'clock. There will be another quiz that will be due. I'll have a quiz due next Tuesday, like on our usual schedule. But because there'll be an exam on Wednesday, I won't have Friday. So the next one after that will be Tuesday. So we'll skip back to next Friday. So what we want to do now, is talk about okay, so I've used this word a little bit. Rn, remember what this is. This is just n-dimensional vectors with real coordinates, right? And what was magic about vectors, right? What makes this a space? How many of you have heard space before in a mathematical context? It's used all over the place. Topological space, vector space, all kinds of spaces. What does it mean to us? Well, a vector space is basically you take two vectors, you got a couple of properties. What happens when you add two vectors? What do you get? You get a new vector, right? What happens when you take a vector and you multiply it by a number? What do you get? Another vector, right? And that's basically it. There's some other things you need for a space, like you need associativity of addition, you need associativity of scalar multiplication, and we went through some of these properties before. So Rn is a space, basically vectors, you can add and subtract vectors, you multiply by scalars, it works nicely. What is a subspace? Well, a subspace is a baby, smaller space perhaps, inside the parent space, so to speak. And I will make that more formal here. Definition. A subspace S and Rn, this is another way. This is being a subset, something inside there. Any subset of S satisfying number one, the zero factor every subspace Rn has to contain zero vectors. Got to be in. And after that, basically all you need is closure under addition and scalar multiplication. So that is to say, if U and V are two vectors, so if you have two vectors that happen to live in this little piece, then when you add them up, it also lives in the little piece. And three, if U is in this subspace and C is in the reals, then CU is in the subspace. That is to say, when you take any vector that's in the subspace and you multiply it by a constant, it's still in there. So basically, here's the rules. Anything's a subspace if you have a zero vector. When you add two vectors in there, it's still in the subspace. And when you multiply any vector in the subspace by any number, it's still in the subspace. Yes. 2, 8. So let me give you a technical point of view. You might think that first one is redundant. because notice the third one says, what happens when I multiply any vector by the constant zero? What do I get? What happens when I multiply any vector by zero? It's a zero vector. So this third one says the zero vector has to be in here, right? Why do I have this first step? Really, this first thing is just to make sure that there is actually something in the subspace that it's not in the first. Okay. Let's look at some examples. I'm going to do a lot of examples of this. Let's take pick any, and by the way, I didn't even specify the number of vectors. You can pick as many as you can pick one vector or 43 null. There's a bunch of vectors all in Rn, then the span of these vectors. Then the span is a subspace. This is a very important example of subspace. And this is called, of course, the subspace span by these. So remember what the span is. All possible linear combinations. So the span is all possible linear combinations of vectors. So a typical element of the span might look like A1, B1 plus A2, B2 plus AK. But you can mix and match those A's however you want, any real numbers you want, and all those possibilities give you what's in the span. Now, let's review. First of all, is the zero vector in the span here? Can anybody think of a way to get the zero vector in there? How could I sagaciously choose these to make sure the zero vector is in there? Yes.
Zero.
Let all the AIs be zero, and what to do? I've got the zero vector in here. Everybody okay with that? What else do I need? I need, if you have two vectors in here, then their sum is in there, right? Well, let's see what two vectors look like. One of them might look like this. There's one of them. I'll call that U. And so I don't use my notation. I'll call that W. There's two vectors in the span. What is U plus V? Or I'm sorry, U plus W. So when I added two thingies in here, I just get another linear combination, right? So I got this way, right? And how about the third one? If I have U is A1, B1, AK, BK, and C is a real number, then CU equals CA1 B1 plus CAK BK. Still, so there's a subspace. So this is a good way to build a subspace. Just pick any number of vectors that you want out of Rn and just see what they span. That'll make a subspace. Everybody okay? Let me give you any questions on that first? Okay. How about R2? So here's a geometric. So here we can kind of see things. Here, what are subspaces? R2. What do they look like? Okay. I did promise to be geometric, so let me draw a picture. Okay, if I have a subspace of R2, what vector for sure has to be in there? Right, I have to have the zero vector, so there's a zero vector, right? Look at that, it's not very big, but it is that problem, zero vector. Okay, suppose that there's some random vector in here. Let me just make something up. Suppose this vector is in my subspace, and it looks a little thin, so I'll straighten it up. Suppose that vector is in subspace. What else has to be in subspace? Any scalar multiple of that, right? Everybody agree? So I can multiply this by 2 and it's going to be in there. Or I can multiply it by 1.5, or I can multiply it by 1.111 or bigger. So what is this? Just if you have the yellow V, you have this entire line. Everybody okay? And that's just from this third property. Everybody agree? What if you have two vectors along this line, like this one and this one? What happens when you add them up? Still on the line, isn't it? Everybody agree with this? Would everybody agree that that line is a subspace? Does it matter what the slope of the line is? I could have any slope, right, including a vertical line, right? And that would be a subspace. So there's a subspace for every possible line. And everybody agree with that? These are all subspaces. Is that it? Is it just the lines? I can actually think of two different subspaces. Might think of another one. If you want to come up with the example, think like a smart. Yeah, points. Which points? Coordinates. No, because you always have to have zero vector. So no matter what, you're always going to have this. Yes.
Would it be some vector that you could add to that to make zero vector?
Right. So his first point is maybe you can throw in another vector u, right? Maybe it's not just multiples of v, maybe it's another one. What happens if you throw in a vector u that's not on that line? What do you think you're going to get? You're actually going to get everything. Everybody agree with that? Because, for example, make something else up like this vector here. Would everybody agree that there's a linear combination of u and v that's going to give you that? In fact, you're probably going to have to make like v negative and then u negative or something like this, right? But you can scale u and v to get this. There's a linear combination of this and be decomposed u and v. If you've done like physics, done like balance diagram, probably done this, and we'll see that with this later. So another space is all that's a space, right? If I take any two-dimensional vector, if I had two-dimensional vectors in R2, what do I get? A two-dimensional vector, right? The zero vector is 0, 0. There you go. And if I multiply a two-dimensional vector by a constant, I get two. Okay, somebody did smart out in the other direction. There's also another space. Yes. Line going which way now? Right, but you'll always get both directions, right? Because you can, whatever direction the line's going, we multiply by negative, and you've got to be able to multiply by negative as well. To also think smaller. Yeah. Well, it's even smaller than that. How about the zero vector by itself, right? This is a subspace in a stupid way. Is the zero vector there? Yes, because I picked it out. What happens if you have two vectors in the subspace? Then they're both the zero vector. And when you add the zero vector to the zero vector, you get the zero vector. What happens if you multiply the zero vector by any constant? Still the zero vector. So in a very silly way, and I'll formalize this right now. Given any space, given any Rn, you will automatically have two silly subspaces. So one thing that you have for sure is you have all of Rn. That'll be a subspace. Any space is a subspace itself, and you will always have the zero vector, which is the smallest space you could ever have because we assume that every subspace contains a zero vector. Okay. Okay. Here's another more exotic example, perhaps. Here's sort of a bigger, this is actually sort of analogous to Rn, but I'm going to think of it in more than one dimension. Let me ask you this. Suppose let me ask you this. If I have an M by N matrix and another M by N matrix, when I add them up, what do I get? Another M by N matrix, right? So when I add two M by N matrices, I get a new M by N matrix, okay? Addition of matrices is associative, like we discussed. What happens when I add the M by N matrix full of all zeros to any matrix? What do I get? The matrix I added it to, right? It doesn't change it, right? What happens if I multiply an M by N matrix by a number? What happens? Right, it just multiplies every entry in that matrix by the same number, and it's a new M by N matrix, right? This is actually also a space, and it is chock full of subspaces. Let me give you an example of a subspace, although you can use your creative mind and come up with lots and lots of it. Let collection of all M by N matrices with leftmost columns. So in other words, so what is a typical element of this collection? Well, I'm gonna write this form. It must be an n by n matrix, so it's got n columns, right? And the first column, the left column is 0. So if I write the matrix in column form, it just looks like that. That's it. It's just got left columns. Right, everything? Okay. I claim that this is a subspace of all n by n matrices. Certainly, this is just a special form of n by n matrix. What do you suppose the zero? What do you suppose plays the role of zero? Right? What is the zero vector for this example? Remember what the zero vector is. Zero vector is the magic vector that you added to any other vector that leaves alone. What's the magic matrix here that you add to anything and it leaves alone? It's zero. The matrix full of zeros. And how would I write that if I was full of energy? I mean, that's kind of silly, but that's what it is, right? It is a matrix with n columns that are all the zero vector, right? Is this thing one of these? You bet. The zero vector or the zero object is in here because all that you need is for the left of those columns to be zero. For this one, all the columns. Everybody okay? What else do we need? We need this to be closed under addition and scalar multiplication. And that's even easier to see. It's the hardest thing is just figuring out what the zero vector for this example is. Suppose what I call U and V are in S. So I'm going to write U this way. 0, V1, V2, V2. And V is 0, V2, V3. Yes.
Why are U and V vectors if they're just matrices of vectors?
It's just a notational thing. So this is what I referred to in the definition. If you look back at the definition, here the notion of vector is actually this huge matrix, right? So you might think of it as a vector that has more coordinates, some more degrees of freedom. What happens if you add these up? What happens? Remember, this is an n by n matrix, right? So to get a new one, you're just adding all the entries, right? So from this perspective, you're just adding the columns, right? So the first column is the zero vector plus the zero vector. What happens when you add the zero vector to itself? The second column should be V2 plus D2. Third column should be V3 plus D3. And the nth column should be Vn plus D. Is this matrix still of the original form? Does it have left column 0? You bet. Right, so it's closed under addition. And what about scalar multiplication? And if C is a real number, then CU is C times the matrix. C is zero vector, C V1, C Vn, which is zero vector CB2, CB3. So when I multiply by a number, I've still got leftmost column 0. So this is a subspace. Any questions? Okay. Definition. Here's another subspace. And this is very important. This one's going to come up in all kinds of applications. This is the column space. So this notation here this is called column space bay, and it is just a subspace of Rm spanned by the column. So just remember that first example we did, we could take any collection of vectors and see what they span, and that always makes a subspace. Well, here, we're just taking a special set of vectors, right? We take a matrix somebody gave me, and I'm gonna just take the columns out, and I'm gonna see what they span. That's gonna be a subspace of Rn. So I'm gonna give you one more example, and then I'm going to show you how to sort of compute some, or not one more example, I'm sorry. Let me give you one more definition and tell you what a basis is after that, and then we'll do some computations. There is a companion to the column space, which is it may look different at first, and we'll make some connections later. Definition. Again, A is just a matrix. It's an n by n matrix. We're going to find the null space of A. And my notation may be open and suggestive. Null A, like that, is the collection of vectors B in such that A, B, C. This is a theme that has come up before, right? This is like solutions to the homogeneous equation. So equivalent. All solutions to the homogeneous equation. So we've done this kind of thing before, right? I mean, we've taken an n by n matrix and we look at the homogeneous equation, and we've got this algorithm where we solve this, right? We row reduce the matrix, and then we say, okay, we've got our free variables, and We've got our basic variables, and we figure out the solution, right? Well, here, these solutions actually form a subspace of Rn. And I'm gonna put my money where my mouth is. Let me show you, because this might be useful to you as well. Let me show you why this is true. Why is null A a subspace? Well, notice that if A and R m by n and AB equals 0 vector, and B, where does B have to lie? Right. And this is a simple question in the following sense. I'm not looking for anything specific here. The only thing I'm asking is, what is the size of B to multiply that matrix A appropriately? If B is a vector, what's its size?
It's gonna be an Rn.
Correct. That is right. A is m by n. B is a vector, so it's something times 1, and it must be n. So B is n Rn. Right? So that's just my gut check to make sure that actually B looks where it's supposed to, and it does on n. What do we have to do for the null A to be a subspace? Well, the first thing is the 0 vector has to live there, right? Everybody agree with that? What happens? What's A times 0 vector? It's always 0 vector. This was perhaps different size. So 0 is in null vector. There you go. The 0 vector's there, so that's my first obstacle that I have come. Okay, to be a subspace, you gotta have a 0 vector living in there. Got that. We also have to have that if U and V live in there, then U plus V lives in there. Okay, let's check that out. And AU and AB are both 0, right? That's what it means for U and V to live there, right? So A of U plus V equals AU plus AB. Well, what are both of these things? They're both 0 because it's in the null space, and 0 plus 0 is 0. So U plus V is in the null space. Okay. That's the second hurdle. If U and V are in the null space, and so is U plus V. And finally, we have to have any scalar multiple of U is in the null space. So again, this means that AU is 0 and C is just any number. If you look at A, CU, this is C, A, because you can pull numbers out of the vector and out of the matrix. And this is C times 0 vector. So we have the null A is subspace. We already showed that the column. We've already showed that the column today is a subspace. I showed that any span is a subspace. And now we've got the null space is also a subspace. Right. And I'm gonna give you, as promised, one last definition, and then I'm gonna do some computations. Definition. Let S be a subspace. Any subspace. Let me point out that S could be all of Rn, or it could be any of our like more exotic subspaces that we looked at earlier. A basis for S is a collection of vectors V1, V2, Vn, okay, such that to be what I call a basis. This is a very special kind of. Have two things. Number one, V1, V2, VK is a linearly independent set. Must be linearly independent. And number two, S must be the span of the vectors. So, what is a basis for a subspace? It's a collection of vectors necessarily in the subspace that is linearly independent, and it spans the entire space. So everything in the space is a linear combination of these vectors, and the vectors are linearly independent. Why do we care about a basis? One of the big reasons we care about a basis is everything in the subspace can be written as a linear combination of these. And when it's linearly independent, also that representation is unique. That is, there's only one way to do it given the basis. So, for example, let me give you kind of an example of basis, but there are many, many others. Notice that everything in R2 can be written on AB, right? AB. A times this plus B times this is what you want, and it's fairly easy to check this linearly independent. In fact, the matrix of this, if you put this together in the matrix, it has two columns in the both pivot columns, so that's linearly independent. Well, this is kind of most of the notation. These EIs and RN are called standard bases. Again, everything in R3 can be written as ABC. So it's A times this plus B times this plus C times that. So it spans all of R3. And again, if you put these in together in a matrix, you make what's called matrix, you've got three bits. So there you go. You can go on. However, these are not the only bases. In fact, any RN has infinitely, any RN has infinitely many bases for n greater than or equal to 1. skills, I guess, but, so another basis for R2, you might check that this is a basis. That's also a basis. It's not as convenient, but it works. Those two vectors are linearly independent, and you can check. It's a good exercise to check that anything in R2 can be written as something times this or something times this. And in fact, that representation will be unique. Let me give you the following matrix here. So let me show you how to find a basis for certain types. Certain example types. Oh, let me also point out that if you have the zero vector space, it has no basis. Well, technically the empty set's the basis, but we're not going to dwell on that too much. That's okay. The following matrix. And for this one, I want to find the basis of the null space. Minus 2, minus 4, 3, minus 7, 7. 1, 2, 1, 1, 4. 4, 8, 3, 5, 15. And 1, 2, what I want to do is I want to find basis. And I'm going to show you the procedure for this. Basically, this is exactly like finding solutions to the homogeneous equation. So we've beaten this one to death many, many times. But I'm going to show you how to pick the basis out of it. So solve the homogeneous equation. So really, I need an augmented matrix, but since it's homogeneous, I'm going to ignore this, and I'm just going to start reducing the matrix, right? The first thing I'm going to do is, I guess I'll take. I guess I'll leave this row alone, 2, 1, 1, 4. And I'm going to use this to kind of nuke everything up and down. So I'm going to multiply this by 2 and add it here. Give me 0, 0, 5, 2 minus 5, 15. I'm going to multiply this by -4 and add it here. 0 minus 1, 1 minus 3. Yes. And I am going to just multiply this by -1 and add it to the bottom. -1, 1 minus 3. Oh, that worked out nicely. So I'm going to put this sucker on the top. 1, 2, 1, 1, 4. And I am going to arrange these rows down here. I'm going to 0, 0, 1 minus 1, 3, 0, 0, 1 minus 1, 3, 0, 0, 1 minus 1, 3. Now, what I did here was I changed the sign here, 1 minus 1, 3, 1 minus 1, 3. And for this one, I divided by 5, 1 minus 1. Everybody okay with that? Now I'm going to take, oh boy, what a lucky fellow I am, right? So now I'm going to use this 1 and I'm going to take everything out. So I'm going to have 0, 0, 1 minus 1, 3. 0, 0, 0, 0, 0, and I'm going to multiply it by -1 and add it up here so I can do my 2. So I can have row reduced echelon form is going to be 0. That's going to be 2. That's going to be. And there I have my row reduced echelon form. Everybody okay with that? Okay, how many basic variables do I have? Good. How many free? I've got 3 free variables corresponding so these corresponding columns, the non-pivot columns. So I guess that would be what, 2, 4, and 5. Everybody okay? So X2, X4, X5 are free, and the other 2 variables, that's one of the next 3, are basic. So I get the following equations. I get the first equation, I get X1 plus 2X2 plus 0X3 plus 2X4 plus X5 equals 0. And I get X3 minus X4 plus 3X5. And so, if I were to write the solution here, and like I said, I'm going to show you here, I pick out the basic. Let's see what this means is X1. Well, so let me fill in what I know. I know that X5 and X4 and X2 are all free, so there's nothing I can do except put it in there. They're my free. Right? What do I know about X3? X3 is X4 minus 3X5. So this is X4. And I know that X1 is minus 2X2 minus 2X4 minus X5. So basically I've got 3 variables. So I've got sort of 3 parameters, and those are essentially like my constants. So I have X2. So if I take this apart piece by piece, let's say I've got a minus 2, a 1, no X2 there, no X2 there, no X2 there. And I've got an X4, minus 2 there, no X4, 1 X4 there, 1 X4 there, no, none there. And the next time, see that's going to be minus 1, no X5, minus 3, no X5. Anybody want to guess for the basis of the null space? Yeah.
Are these 3 vectors it?
That's exactly right. It's just these 3 vectors here. So it should be minus 2, 1, 0, 0, 0. Minus 2, 0, 1, 1, 0. And minus 1, 0, 1, 3, 0. So it's basically the vectors that multiply your free parameters are exactly what give you the basis for your null space. Let me leave you with an exercise. I didn't get quite where I wanted, but I'm going to finish this up next time. Let me turn this on its head. So see if you can do this. The column space of 1, 1, 4, 5, 11, 0, 4, 6, 11. See if you can find a basis for the column space. The procedure on this is very much similar. What you do is reduce the matrix and use the pivot columns. But don't use the pivot columns on the reduced matrix. You have to find which pivot columns in the original matrix by reducing and use the original pivot column. See if you can work your way through that, and I will go through this explicitly next time. Okay, question. Question. Your quiz will come live like sometime this afternoon. It's due Friday. The big question will be in my office. Y'all have to.